In the summer of 1977, two spacecraft left Earth on a mission unlike anything humanity had attempted before. They carried no crew, no expectation of return, and no guarantee they would survive the harsh environment beyond the asteroid belt. Yet those twin explorers would go on to transform our understanding of the solar system and become the most distant human-made objects ever created. They were Voyager 1 and Voyager 2. At first glance, they looked modest compared with today's sophisticated spacecraft. But hidden beneath their metal frames were cameras, scientific instruments, and an ambitious goal: to take advantage of an exceptionally rare alignment of the giant planets. For a brief window in history, Jupiter, Saturn, Uranus, and Neptune were positioned so that a single sequence of gravity assists could carry a spacecraft from one world to the next. Such an opportunity comes only once every century and a half. NASA realized that missing this alignment would delay a similar mission for generations. Engineers designed the Voyagers to seize that opportunity, turning the immense gravity of each planet into a natural slingshot that accelerated the probes toward the next destination without requiring enormous amounts of fuel. Voyager 2 launched first on August 20, 1977, while Voyager 1 followed just over 2 weeks later on September 5. Despite its name, Voyager 1 traveled along a faster trajectory, allowing it to reach Jupiter ahead of its twin. Even before arriving at the giant planets, the spacecraft offered a new perspective on our place in space. Looking back toward Earth, they photographed the planet shrinking into the darkness. It was an early reminder that everything humanity had ever known existed on one small world drifting around an ordinary star. When Voyager 1 reached Jupiter in 1979, scientists expected impressive photographs. What they received was a complete reintroduction to the largest planet in the solar system. Instead of a calm striped sphere, Jupiter revealed itself as an atmosphere in constant motion. Towering cloud systems stretched for thousands of kilometers. Powerful jet streams wrapped around the planet at incredible speeds. Storms collided, merged, and evolved across layers of swirling gases, creating a landscape unlike anything seen on Earth. The Great Red Spot, already famous through telescopic observations, became even more extraordinary when viewed close up. Far from being a simple red stain, it proved to be a colossal storm system larger than our own planet, rotating continuously for centuries while surrounded by countless smaller vortices. Yet Jupiter itself was only part of the story. One of Voyager's greatest surprises came from a moon that many believed would be cold, ancient, and inactive. Instead, Io stunned scientists by becoming the first world beyond Earth where active volcanoes were directly observed. Gigantic plumes erupted hundreds of kilometers above the surface. Rivers of molten material reshaped the landscape. Sulfur compounds painted the moon in brilliant shades of yellow, orange, red, and black. Rather than a frozen relic from the solar system's formation, Io turned out to be the most volcanically active body ever discovered. Not far away, another moon hinted at a very different mystery. Europa appeared smooth and bright, covered by an intricate network of long fractures stretching across its icy shell. Surprisingly few impact craters suggested that its surface was constantly being renewed. Those observations inspired a remarkable possibility. Beneath the frozen crust could lie a global ocean of liquid water kept warm by tidal forces generated through Jupiter's immense gravity. That single idea changed the direction of planetary science. A moon once considered little more than an icy satellite suddenly became one of the most promising locations in the search for environments capable of supporting life. After Jupiter, the Voyagers continued toward Saturn, a world already celebrated for its magnificent rings. Astronomers had admired those rings for centuries, but only close inspection revealed their astonishing complexity. Instead of broad, simple bands, the rings consisted of thousands of delicate ringlets separated by narrow gaps, braided structures, and constantly changing patterns. Tiny moons acted as gravitational shepherds, maintaining the shapes of certain rings while sculpting others into intricate formations. Every new image revealed another level of detail, demonstrating that Saturn's rings were dynamic systems rather than static decorations surrounding the planet. Saturn's largest moon, Titan, also emerged as one of the mission's greatest scientific prizes. Wrapped in a dense orange atmosphere, Titan concealed its surface completely from Voyager's cameras. Scientists measured an atmosphere dominated by nitrogen, making Titan unique among known moons and setting the stage for future missions that would eventually uncover lakes and rivers of liquid hydrocarbons on its surface. By the time Voyager completed its encounters with Jupiter and Saturn, one fact had become impossible to ignore. The outer solar system was not a quiet collection of frozen worlds. It was a diverse and active region filled with volcanic moons, hidden oceans, complex atmospheres, powerful storms, and geological processes unlike anything previously imagined. The farther humanity explored, the stranger the solar system became, and Voyager's greatest discoveries were still waiting farther ahead. After completing its encounter with Saturn, Voyager 1 was redirected onto a trajectory that would eventually carry it out of the plane of the solar system. Its close flyby of Titan had provided invaluable scientific data, but it also meant the spacecraft would not continue to Uranus or Neptune. That responsibility fell entirely to Voyager 2, which pressed onward into territory no spacecraft had ever explored. In January 1986, Voyager 2 arrived at Uranus, a planet unlike any other. Rather than spinning upright like Earth or Jupiter, Uranus rotates almost completely on its side, as though an ancient collision had knocked the planet over billions of years ago. This unusual orientation creates seasons unlike anywhere else in the solar system, with each pole spending decades in continuous sunlight followed by decades of darkness. From a distance, Uranus appeared calm, almost featureless. Its pale blue atmosphere lacked the dramatic bands and giant storms visible on Jupiter and Saturn. But Voyager's instruments revealed that beneath this quiet appearance was a remarkably unusual magnetic field. Instead of being centered within the planet and aligned with its rotation, the magnetic field was tilted and displaced, producing a constantly changing magnetosphere unlike anything previously observed. The mission also discovered new moons and previously unknown rings encircling the planet. Among those moons, Miranda immediately captured scientists' attention. Its surface looked as though enormous pieces from different worlds had been stitched together into a single body. Towering cliffs, deep valleys, and bizarre geological formations hinted at a violent past that researchers are still trying to understand today. 3 years later, Voyager 2 reached its final planetary destination. Neptune lies so far from the Sun that daylight there is hundreds of times dimmer than on Earth. Many expected a quiet, frozen world with little atmospheric activity. Instead, Neptune delivered another surprise. The spacecraft found one of the most dynamic atmospheres in the solar system. Powerful winds raced around the planet at speeds exceeding 2,000 kilometers per hour, making them the fastest planetary winds ever measured. Massive storms drifted through the atmosphere, including the enormous Great Dark Spot, demonstrating that even at the edge of the Sun's influence, planetary weather could be astonishingly energetic. Neptune's faint rings also proved more complicated than expected. Rather than forming perfectly uniform circles, parts of the rings appeared brighter than others, creating mysterious arcs that challenged existing ideas about how planetary rings remain stable over long periods.